All right, as you're watching this video, hopefully you are only watching as much as you need. At any point during the question, if you can move on and solve the rest on your own, you should probably stop and try to do so. I only want you to watch what you have to help you with the problem, all right? So number one is asking what open intervals a function is increasing and decreasing. So if I'm looking for increase and decreases, I'm interested in my derivative. And I'm interested in if my derivative is positive, if it's greater than 0, that means I'm increasing. If my derivative is negative, that means I am decreasing. I also know that when my derivative is 0, that is when I could change from increasing to decreasing or the other way around. So the first thing I want to do is take my derivative. So f prime of x equals the quotient rule. The top is the derivative of the top, 0, multiplied by the bottom, minus the derivative of the bottom, which is 2x, multiplied by the top, which is 1. All of that gets divided by x squared minus 36 squared. I have to square the bottom with the quotient rule. So this is not as ugly as it seems, f prime of x. The top, the 0 goes away, and I just end up with negative 2x on top, and x squared minus 36 squared on the bottom. So it's not too messy of a derivative, but I am interested in where it equals 0, and I should have also put where it doesn't exist or is undefined, because at those places, at those x values, I could also get a change from increase to decrease. So let's check that. Let's find what makes my function equal 0. Well, the bottom can't equal 0, so let's let the top equal 0, and that's going to happen when x is 0. So that's one of my important critical values. The other value I'm interested in is when the bottom, I'm not supposed to let the bottom equal 0. That's when I'm going to be undefined. So let's set it equal to 0 and find out what makes that happen. So if I square root both sides, I get x squared minus 36 equals 0. And that means that x squared equals 36. So x could be positive 6 or negative 6. So I also want to check what's happening around those values, because I could possibly change my increase and decrease. So the way that I check my intervals is I make a table, right? We put 0 in the middle, negative 6 to the left, 6 to the right, and I'm just going to pick values in between these. So negative 7, negative 1, 1, and 7. And I'm not interested in what's happening at negative 6, 0, and 6. I want to know, because at negative 6, I know I don't have a slope. It's either undefined or at 0. So I want to see what is happening up until I get to negative 6. So I plug negative 7 into my derivative right here. And when I do that, I'm going to get a fraction. On the top, a negative 7 and a negative 2 are going to give me a positive number on top. And on the bottom, well, it doesn't matter what I plug in. I'm going to square it, and that's going to also give me a positive. So up until I get to negative 6, I'm positive. My function is increasing because I have a positive slope. Well, let's plug in negative 1. When I plug in negative 1, on top, I get a positive. When I plug in negative 1 on the bottom, everything turns into a positive. So positive over a positive, I end up with a positive value. I don't really care what the value is. I just care that it's positive, because that tells me I'm increasing. When I plug in a 1, my top is a negative, my bottom is still a positive, so I'm actually decreasing at 1. And same thing with 7. The top's going to be a negative, the bottom's going to be a positive, so I'm also decreasing when I'm at 7. So what this tells me is from negative infinity up until negative 6, my function is increasing because it's positive. But it's also increasing from negative 6 up until I get to 0. I don't know what's happening at negative 6, nothing good, But I do know that from negative infinity to negative 6, I'm increasing, and the same from negative 6 to 0. Now from 0 to 6, my function is decreasing because it's a negative derivative. And from 6 to infinity, my function is also decreasing. If you're not sure, graph the original function in your calculator and you will see that that's true. You've got those inflection points, or those, not inflection points, but you've got those tangents that are making the negative 6 and at 6, where we don't change from increase to decrease, we just keep going. But you're going to see that picture. You'll be able to see that increase and decrease when you graph it. All right, number 2. A function has, we got to erase more stuff. A function has critical numbers of 0, 4, and negative 2. That's nice. So they already give me my critical values. And then it tells me, it gives me my second derivative, and it wants to know which critical numbers, if any, are minimums or maximums. Okay, so I know a couple things about critical numbers. I know that my slope is 0. So I could be concave down. I could be concave up. I could also be increasing and then still increase. So I could have a slope of 0, but at that point, I'm not concave up or concave down. So those are the 3 options, right? I could be one of those 3, and the second derivative tells me which one of them I am. So if I take the second derivative of 0 and I plug it in, 3 times 0 squared minus 4 times 0 minus 8. That gives me what? Negative 8. So my second derivative at the point 0 is a negative. That tells me my original function is concave down. If your second derivative is a negative, you're concave down, which means that this point up here is a maximum. So 0, x equals 0, gives me a maximum. So now I do the same thing, but this time I'm going to plug in a 4 and see what happens. When I plug in a 4, let's see, 4 squared is 16 times 3 is 48, minus 16 minus 8, so that's going to give me 24, which is positive. So at 4, my original function is positive, which means it's concave up, which tells me that at that point, I have a relative minimum at x equals 4. And if I plug in a negative 2, I'm assuming I might get a 0 here. Let's see. Negative 2 squared is 4 times 3 is 12. Negative 4 times negative 2, nope, I'm not going to. That's 8 minus 8. So this becomes 12, which is positive, which again means I'm concave up. So that means that negative 2 has a relative minimum. So I can say that f of x has a relative minimum at x equals 4 and at x equals negative 2. F of x has a relative maximum at x equals, what was it, 0. And the second derivative gives me all of that information. Okay, number 3. Get some of this out of the way. Maybe. What's going on? We'll get lots of it out of the way. So number 3, if b of x equals f of x squared times g of x, then b prime of negative 4, and then it gives me a table to use. So let's take the derivative of b prime. So b prime equals, let's see, I've got 2 functions, so I've got to do the product rule. The derivative of the first is 2f of x, and then I have to times by the second, times g of x, plus the derivative of the second is, I'm missing something right there. The derivative, I did the derivative of the outside, but I need to multiply by the derivative of the inside. Don't forget the chain rule. Then I've got my g of x. So there's a lot getting multiplied right there. Plus, the derivative of g is g prime of x multiplied by the original f of x squared. So now it wants me to find b prime of 4. So 2 multiplied by f of 4. So I'm looking at, negative 4, sorry. I am looking at this row right here. I'm looking at my negative 4s. So f of negative 4 is 1. F prime of negative 4 is 2. G of negative 4 is negative 6. And then I'm going to add g prime of negative 4 is negative 4. And f of negative 4 was 1, and I'm going to square that. So 2 times 2 is 4, times negative 6 is negative 24. Negative 4 times 1 squared is just negative 4. So I get negative 28 would be my answer. Okay, number 4, it wants us to use the graph above. We're going from 0 to 6, and I'm going to use this to answer some questions, some true and false questions. So first thing I need to keep in mind, this graph is my derivative graph. So this represents the slopes of f. So this graph gives me my slopes of f of x. Okay, this is not a graph of f, this is a graph of f prime. So this tells me, part A, f is discontinuous at x equals 2, which is right here, and x equals 4. Well, all I know about f, looking at 2, is that at the point 2, f has a slope of negative 5. But it has a slope, which means it is continuous because it has a slope of negative 5. And at 4, all I know is that I have a slope of negative 2. I don't know what else is going on, but I have a slope of negative 2, which means it is not discontinuous. So A is going to be false, all right? Now B, f is decreasing from 2 to 4. So that tells me that f, my original function, should be going down, which means I would have a negative slope. Well, if I look at my graph from 2 all the way to 3.5, my picture is negative, but these are pictures of my slope values. So from 2 to 3.5, my slope is actually increasing. My function is actually increasing. So that one is also false. I am decreasing whenever my slope is under the negative. So part C, f is constant from 4 to 6. If f is constant, if my original function is constant and not going up or down, I would have a slope of 0. But from 4 to 6, this tells me that I have a slope of negative 2. From 4 to 6, it says even though the f prime is flat, my original function has a constant slope of negative 2. So that one is also false. I'm noticing a pattern here. D, f has a local relative maximum at 3.5. So let's get rid of some of this. A local relative maximum at 3.5. Okay, so to have a maximum, my derivative should be 0, which it is. And to have a maximum, if you think about a maximum, I have a positive slope and then it turns into a negative slope. That's what gives me a maximum. So if I look at my graph here, my slope is positive, 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 positive until I get to 3.5, and then it's negative. So I would say that is true. I do have a maximum because I have a positive slope and then it turns into a negative slope, which gives me a relative maximum. So f has a relative minimum at 3.5. Well, I can't have a relative minimum because I had a relative maximum. So I know that one's false. F has a local maximum at x equals 2. So let's see what's happening at 2. So x equals 2 is right here. And I would say that f prime has a maximum, but what do I know about my actual function f? I know that the maximums have to happen when my slope is 0. My slope has to be 0. Well, that slope at 2, my slope is -5. So my slope is definitely not 0. So I would say false. And then G, f is increasing from 0 all the way to 4.5. So from 0, as I go along, I have positive, 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 positive. But when I get to 3.5, my slopes become negative values. So f is not increasing. It is increasing from 0 till 3.5, but from 3.5 all the way up to 6, I'm actually decreasing because I have negative slopes. Okay, number 5. What does number 5 want? What must be true about the function in f, the function f in terms of concavity and points of inflection? So what must be true given this graph, the derivative graph? What must be true about the function in terms of concavity and the points of inflection? Okay, so to find concavity, concavity and points of inflection, that has to do with my second derivative, right? So what I know is to get my second derivative, to get to my second derivative from my first derivative graph, I've got to look at the slopes. So the slope of my derivative graph, my slope is positive right here. I'm going up. Now, I'm not looking at my y values. I'm looking at the actual graph this time because I'm moving up to my second derivative. So I am positive. My slope is positive from what? 0 until I get to 2. I have a positive slope, which means my f double prime is going to be greater than 0, which means I'm going to be concave up. Then from 2 all the way until I get to 4, from 2 to 4, I have a negative slope. So that tells me that my f double prime is going to be less than 0, which tells me that I'm going to be concave down. And then what is happening from 4 to 6? I have no slope. My slope is 0. So I'm not going to be concave up or down because I have a... Well, I guess from here, we don't know what's going on. All I know is my second derivative is going to be 0, and I can't use my second derivative to tell me anything when it is equal to 0, other than that there's inflection points. So that's all I can say about concavity. Now, my inflection points happen when my derivative, my second derivative, is equal to 0, right? Or does not exist. That's when I get inflection points. So if I look at where is my derivative 0 or doesn't exist, and I've got that right here at 2. At 2, I have a slope that does not exist. But I do know that before that point, I'm concave up. So I'm concave up until I get to 2. And then after that, I'm concave down. So that means that I have a point of inflection. So that right there, x equals 2, is an inflection point because I change concavity. At 4, I'm concave down until I get to 4. But when I get to 4, I don't change to being a positive slope. My slope becomes 0. So that means I just keep going at the same, my slope doesn't change, which doesn't make it a point of inflection. It's only a point of inflection if the slope or concavity changes from positive to negative. So that's all I can say about inflections, is there's only one of those at x equals 2. Okay, let's move on. More graph questions. Lucky you. This is the same graph from before, but this time it's labeled as velocity. So that means that it's still a derivative graph, right? Because it's still the velocity. And my values across the bottom are in seconds. So 6 wants to know at what t value does the acceleration change sign? So when does the acceleration change sign? Now I am looking at my velocity graph. Now the derivative of my velocity graph, remember acceleration is velocity prime. So I want to know when does velocity prime, when does it change from positive to negative, or when does it change signs? And that happens when my slope changes from positive to negative or from negative to positive. So if I look at my picture, my slope is going up until I hit 2, and then I have a negative slope. So at t equals 2, my acceleration changes because my slope changes. So my acceleration changes. Signs. I should put signs after that, huh? But at 4, my slope is negative, and then my slope turns into 0. So I go from a negative slope to a 0 slope, which does not mean I change signs. I only change signs when it actually goes from a negative to a positive or a positive to a negative. So t equals 2 would be the only place that I change, my acceleration changes signs. Okay, number 7, the acceleration of the particle is negative for what time interval? Well, my acceleration is negative whenever my slope is negative of this graph, because this is my velocity. So I want to know, when do I have a negative slope? Well, I have a negative slope from 2 until I get to 4. So from 2 to 4, my acceleration is negative because the slope of the velocity is negative. When does the object change direction? Well, my object changes direction when my velocity changes signs. My object changes direction when my velocity goes from a positive to a negative or a negative to a positive. Now, I've got to be careful because I'm not looking at the slopes. I'm looking at my values of velocity. So right here, I have positive velocity, positive velocity, positive, 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 positive. And then right here at 3.5, I go from a positive velocity to a negative velocity, which means I am changing direction. So at t equals 3.5 or about 3.5, that's about as close as I can get. That is where I change signs. Number 9, what is the t value when the particle is furthest to the left and furthest to the right? Okay, so if I'm looking at furthest to the left and furthest to the right, I'm interested in my position. When is my position furthest left, furthest right? So we are interested in a couple of things. We are interested in when, where did my pen go? When f prime of x is equal to 0, that's when I go from a positive slope to a negative slope. So that means my original function is changing direction, okay? So if I look at my velocity graph, when I start right here, I'm positive. My velocity is positive. So that means I'm moving to the right. And then when I get to 2, I'm still positive. In fact, I'm still moving to the right all the way down until I get to a velocity of 0. I'm moving to the right all the way until 3.5. And then at 3.5, my velocity goes to 0. And it becomes negative, which means I start moving to the left. So that tells me that I am furthest to the right at this point right here. I've gone to the right the furthest at 3.5. So I would say when t equals 3.5, I'm furthest right. Now you just have to decide. I started clear over here, and I went to the right a whole bunch, and then I started coming back to the left. So you just have to decide, between 3.5 and 6, did you come back to the left far enough to pass where you started? And if you look at the graph, we haven't technically learned area under the curve, but look at all of this area that you moved, right? This is the area that you covered when you were moving to the right. And then you get to 3.5 and you stop and you start going to the left. Well, when I look at this graph, it looks like I went a lot more to the right than I did to the left. So I would say that I'm furthest left when my time was equal to 0. I don't think I went left far enough to get back to where I started. So I would be furthest left when time is 0. Okay, number 10. The objects, we are still using the graph up here. The object's average acceleration for the interval from 3 to 5. Ooh, this is a good question. If I'm looking for average acceleration, remember, when I'm looking for average anything, we're using our slope formula, which is my y2 minus y1 over x2 minus x1. So I want my average acceleration, which means I want to use my derivative values. I want to use my velocity values when I plug into this formula. So we're going from 3 to 5. So those are my x's. I know that my x is 3 and 5. But when I plug in a 3 up here, at 3, I'm at what? 1.5. So when I plug in a 3, my y value is 1.5. When I plug in a 5, my y value is down here at -2. So what do I get? 1.5 plus 2 divided by -2. So that's what? 3.5 divided by -2. And if we want to actually finish that out, we would say -1.75. And my units, it gave me my units, right? Feet per second squared. It gave it to us. It didn't ask us to use the units. It gave them to us, so we're going to plug them in right there. I didn't have to come up with those on my own. It just told me what my units would be. Okay, number 11. We can kind of move on from the graph. The maximum value of the function on -2 to 4 is. Okay, so it gives us a function. It wants us to find the maximum value. It doesn't care where it happens. It just wants the maximum value. It wants the biggest y value we get. Well, I know that's going to happen in certain places. It's either going to happen at the endpoints, or it's going to happen when y prime equals 0. Those are going to be my possible, and I guess technically where it's also undefined, but we're not going to have to deal with that on this question. But those are where I could get a maximum. So first things first, let's get y prime. So y prime is going to be what? 9x squared plus 4x minus 1. And the plus 1 goes away. So that looks good to me. To find my zeros, this is not going to... Is it going to factor nicely? No, because I'm going to end up with a -9 on top and a 4 on the bottom. So this isn't going to factor nicely. So you have a couple options. You can put this in your calculator. You can graph it, or you can use the polysmelt on the calculator. I guess either way you're using the calculator. But let's go to y equals and let's just graph this one. My slope was 9x squared. I hope. And then it was plus 4x and then minus 1, I think. And then I want to know where that is going to equal 0. So when I graph it, it's going to equal, actually, let's change our window because we're only going from, now I've got to double check. We're going from -2 up to 4. So I'm going to change my window. My x minimum I want to be -2. And my x maximum I want to be 4. And now let's graph it. Okay, so I've got 2 zeros. So if I go second, calculate zeros, I want to get near the first one. So I'm going to move over near this one right here. Enter, enter. What happened to my calculate? I can't remember if calculate zeros works on this one or not. I feel like it doesn't work very good. Oh, maybe it just finds it. Oh, it wants me to left bound and right bound. Okay, so my 0 is at about -5.94. Am I comfortable with that number? That doesn't seem close enough. So let's calculate intersections instead. Let's see if that works. Yours works better than mine. Mine is a free version. It doesn't work super good. There we go. I like that better. -0.623. So I'm going to go back here. So I have a when x equals -0.623. And then let's find my other 0. So let's do second calculate, intersect. And we're going to go back over here, to the left, to the right. And I get 0.178. I guess this is probably what I should have been doing before. That's why I graphed the y equals 0. So x equals, oh, now I can't remember what it is, 0.178. Yeah. And I also want to check my endpoints, -2 and 4. So when I plug these values in, I'm just going to go back to my calculator, and I'm going to go to the table, and I want to plug in all of those values. So I want to plug in -2, and I want to plug in -0.623, and I want to plug in 0.178, and I want to plug in a 4. And it's just asking for the maximum. So when I look at those values, that's not what I wanted to plug it into. I'm plugging them into my derivative. I need to plug them into my original function. So let's rewrite our original function real quick. 3x raised to the third power, and then it was plus 2x squared, and then it was minus x, and I think it was plus 1. Let's double check. Plus 1. Okay. Now I'm okay to use my table. So I want -0.623. I want -2. I want 0.178, and I want 4. So I've got 1.68 or 1.67. That's not very high. -13 is really low. 0.9 is low. 221 is my biggest y value. So I would go back, because it just wants my maximum. I would say the maximum value is 221. It doesn't ask where it happens. It just wants the maximum value. Okay, number 12. What is the total number of extrema for the function whose derivative for all x is f prime equals x times x squared plus 9 times x minus 5 squared? So it already gave me the derivative. And I know that extrema happens when my derivative equals 0. So if I rewrite this, 0 equals x times x squared plus 9 times x minus 5 squared, I have a bunch of values that could possibly be 0. So any of these three could multiply and be 0. So x could be 0. This middle one right here, x squared plus 9, it doesn't matter what x is. I'm going to square it, and then I'm going to add 9. There's no way to get a 0. There's no way to get to 0 with that one, at least not with real numbers, and that's all we're working with. Now, the other option would be x minus 5 squared equaling 0. So x minus 5 would equal 0, so x would equal 5. So I need to check around these 2 points. Now, remember, these are possible extrema. These are my critical values. X equals 0 and 5 are critical values. But I don't know if they're max or minimums until I make my chart and check and see what's happening around these values. So let's check -1, 1, and 6. So when I plug in a -1, can we do this without actually having to do the math? When I plug a -1 in, I get a negative. Well, what do I get? I get a negative, and then x squared plus 9 becomes a positive. So I do a negative times a positive. X minus 5 gets squared, and it becomes a positive. So -1 gives me a negative answer. When I plug in a +1, I get a positive, positive, positive. So that's going to be positive, and 6, when I plug it in, I'm also going to get a positive, positive, positive. When I multiply those together, I get a positive. Again, I know I'm not looking at the numbers specifically. I don't care about the numbers. I just want to know, am I increasing or decreasing right now? And this told me from -1 up to 0, my function is going down. Where'd my pen go? I'm going down, and then at 0, I start going up. And then at 5, I kind of level out, but I keep going up after 5. So I only have an extrema right there at 0. So I only have one extrema when x equals 0. I get a relative minimum. That's my only extrema. Okay, number 13. Man, I am having to squish stuff in here. I should really just use more paper, cut down more trees, give you more space. Number 13, what is the minimum value of the function y equals -3 cosine x plus 3 sine of 2x on the interval from 0 to 2 pi? So again, it is asking for a minimum value, not relative minimum. So it is asking for the absolute minimum. So I want to check where y prime equals 0 or is undefined, and I want to check my endpoints. And I want to see what the values are at all of those places. And when I do, it's going to tell me what the values are. And then I just have to pick the minimum of those values. So first things first, let's get y prime. So the derivative of -3 cosine x. Well, the derivative of cosine is negative sine. So that's going to take my -3 and turn it into a +3. So I get 3 sine x. And then the derivative of 3 sine of 2x. Well, the derivative of the outside is going to be 3 cosine 2x. But then I have to multiply by the derivative of the inside, which is 2. And I think that should do it. So if I rewrite this, y prime equals 3 sine of x plus 6 cosine 2x. I just multiplied that 2 to the front. So now that I have my derivative, I need to find, it's not going to be undefined anywhere, but I do want to know where does that equal 0. And I want to know, well, I already know my endpoints, so I'll check them after. So let's find out where does this equal 0. And to do that, I'm going to go to my calculator. I'm going to go to y equals, and I am going to plug in my derivative. So 3 sine of regular x, and then I'm going to add 6 cosine of 2x. And I want to know when this is equal to 0. Now, before I look at the graph, there's 2 things I want to double check. First of all, my window. I want to go from 0 to 2 pi. So I'm going to change my window 0 to 2 pi. The other thing I want to make sure is that I'm in radian mode, because I'm doing sines and cosines. I don't want to be using degrees. So if I go down, if I hit mode, I go down to radian degree and I make sure degree is highlighted. Now I can look at the graph and there's a lot going on, right? So this is, what is this the graph of? This is the graph of my derivative. So as I go from the left to the right, I have, see if I can show you this. I know my picture has a negative slope, but this represents the slopes of my function. So I have a positive slope right now, and then right here I get a slope of 0. And then my slope becomes negative. So what that means is I'm going up, 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 and then I'm going down, down, down. Now, if I'm looking for a minimum, that's not going to happen right here, because right here I'm going up and then I stop and then I go down. That's going to be a relative maximum, not a minimum. So I don't even care about checking that 0. Now my function is going down and it starts going up right here. That is a 0 I'm going to want to check. So maybe we should do that right now. Let's go second, calculate intersections. And I want this intersection right here. So that happens at 2.1386. So we'll say 2.139. So I'm going to go back here and I'm going to want to check x equals 2.139. That's one point I'm interested in. Now my function is positive again. So I'm going up, 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 and now my slope is 0 and I'm going down. So that means this 0 right here is another relative maximum, because I'm going positive to negative. So I'm not even going to check that. I want to know when I go from a negative to a positive. So I'm negative, negative, negative. Right here I go from a negative to a positive slope. So I'm interested in that intersection as well. So let's second calculate the intersection, and we're going to go here and here. So we've got 5.648. 5.648. So x equals 5.648. Now I also need to check my endpoints. So x equals 0 and x equals 2 pi, because it wants the minimum value, not a relative minimum. It wants that absolute minimum value. So let's plug these in. We're going to plug them back into our original function. So on my calculator, I'm not going to make the mistake of plugging them into my derivative. Where did my y equals go? Stop it. What's going on? There we go. My original function was what? -3 cosine of x plus 3 sine of 2x. I hope. And let's go to the table, second table. So I wanted to check 0. I also wanted to check some weird numbers. 2.139. 2.139. I also wanted to check 5 something. 5.648. 5.648. And then I also wanted to check 2 pi. So what I'm looking for is my minimum value, my smallest y value. And I've got -3, -1, -5, -3. So my minimum happens at 5.648. I get a minimum of -5.28. So what does the question ask me? What is the minimum value? So at x equals 5.648, f of x has a minimum, or y, I guess I should say y, because my function is y. Y has a minimum of negative, and now I don't remember what it was. Negative 5.28. Probably 5.281. Negative 5.281. So y has a minimum of negative 5.281. That's all the question's asking. Sometimes this part doesn't hurt to have written in there, just to kind of solidify the right answer. All right, number 14. Get some of this out of our way. The graph of the differentiable function is shown. Arrange each of the following from least to greatest. Oh, I like this one. Okay, so I am first looking at the point negative 3. So I'm looking right here. F of negative 3. Well, let's see. F of negative 3, my value is what? 1, 2, 3, 4, 5, 6. So F of negative 3, I get a value of 6-ish. The derivative at negative 3. So my slope at negative 3, remember derivative represents slope. So my slope at negative 3 is actually 0 because that's a maximum. So I have a slope of 0 at f prime of negative 3. F double prime of negative 3, well, f double prime is my concavity. And if I look at my picture right there, I am definitely concave down. I don't know what my value is specifically, but I do know that it is absolutely negative. So that means the smallest of these three, f double prime of negative 3 is going to be the smallest, and then f prime of negative 3, and then f of negative 3 is going to be the greatest. So let's do the same thing for part B. B says f of 0.5, which is right about here. So f of 0.5, that value, let's call that negative 1. Maybe not quite 1, maybe it's 3/4, but it's close. F prime, my slope right there, again, my slope is 0 because that's a minimum. And my second derivative, this time I'm concave up. So I don't know what that value is, but I do know it's positive, which gives me enough information to order these. So my smallest this time is f of 0.5. Then I get f prime of 0.5, and then I get f double prime of 0.5. Again, even though I don't know the value, I know it's positive, so it's definitely bigger than f prime and f, because those are 0 and negative 1. All right, 15. A point moves along the curve y equals 2x squared minus 1 in such a way that the y value is decreasing at a rate of 2. Okay, so right now I'm going to write dy dt is decreasing by 2. At what rate is x changing? So what is dx dt when x equals negative 1.5? So x equals negative 1.5. Well, it gives me a function, y equals 2x squared minus 1. Let's take the derivative. Dy dt equals 4x dx dt, and the minus 1 goes away. So plug in our numbers. I know dy dt, so that becomes negative 2. I already know 4 because it tells me 4. X is negative 1.5. And dx dt is here. So I'm trying to get dx dt alone. So 4 times negative 1.5, that's going to be negative 6, right? And I'm going to divide that over to get dx dt alone. So I got negative 2 over negative 6 equals dx dt. So dx dt, my change is going to be 1/3. So that means I'm changing, when y is changing at a rate of 2 units per second, x is changing at a rate of 1/3 units per second. Cool. We like those ones. So let's do some more. At the top of a ladder, of course there's a ladder question, is sliding down a vertical wall. So here is my vertical wall, and here is my, you know what? We're not going to do a blue ladder. We're going to do a brown ladder. I don't know why. It's not changing, so we'll pretend it's like made of wood. So we know that the ladder is 20 feet. And I know that it is sliding down the vertical wall. And out of habit, if I have something vertical, I usually call it Y and the horizontal X. So I know that I am changing at a rate of -2 because my ladder is going down the wall. So dy dt is -2 when the top of the ladder is 8 feet from the ground. So when the top of the ladder is here, and that means my y is 8. When the top of the ladder is 8 feet from the ground, what is the rate of change from the distance between the bottom of the ladder and the wall? So what is dx dt? That's what it wants to know. Well, I know a formula with x and y and my hypotenuse ladder, right? X squared plus y squared equals 20 squared. And if I take the derivative of this function, I get 2x dx dt plus 2y dy dt equals nothing, equals 0. The derivative of 20 squared is 0. We don't even care what that number is. Now, I have a dy dt to plug in. I know what that is. I know what my y is, and I know what my 2's are. I'm missing x. I don't know what x is. So I actually need to solve. If I do, let's see, x squared plus 8 squared equals 20 squared. I actually need to solve this. So x squared plus 64 equals 400. So x squared equals 336. So x equals the square root of 336. And I'm not worried about the negative square root because this is a distance. You can't have a negative distance. So I know it's going to be the positive square root. Let's just plug that in like it is to my x value. So I get 2 times the square root of 336 dx dt plus, I am running out of room. Let's move this over here. And now we've got this messy thing in the way. Plus 2, and my y value is 8. My dy dt is -2 equals 0. So this becomes 2 root 336 dx dt, not plus. What is that? -16 times 2, so -32. So let's just add that to the other side and make it positive 32. So then my dx dt equals 32 divided by 2 root 336, which becomes dx dt, 32 divided by 2 is 16 over root 336. And I don't think that's a nice number. What is it? Let's go back here. What's the root? Nope, get rid of you. What's my root of 336? Yeah, it's not a nice number. So go ahead and leave it like that. That's a great answer right there. No decimals, please. 17, which is covered with a mess. Okay, 17. The radius of a circle is increasing at the rate of 3 feet per minute. So dr dt equals 3. Find the rate which the area is increasing. So it wants me to find dA dt when my radius equals 10. All right, so I need the derivative of area. So let's start with area. The area of a circle equals pi r squared. So I need to take the derivative. So the derivative of the area equals 2 pi r dr dt. And I think I know everything, don't I? I know dr dt. So dA dt equals, I know the 2, I know the pi, I know the radius, 10, and I know dr dt, which was 3. So dA dt equals 2 times 10 is 20, times 3 is 60, so 60 pi. And I don't think you need to multiply pi in. In fact, on the AP test, if this was not multiple choice, you could have just left that right there. But we'll take 60 pi as the correct answer. Number 18, if f is continuous function on the closed interval -2 to 1, and f of -2 is 8, and f of 1 is -10. Okay, hold on. Let's draw a picture. It's a lot going on. Okay, I am going from -2 to +1. And I know that f of -2 is +8. So 1, 2, 3, 4, 5, 6, 7, 8. So I start up here, and f of 1 is -10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So f of 1 is down here. That's all I know. Oh, I know it's continuous. So f could be a lot of things. F could be a straight line that goes like that. F could also be something that like goes up and goes down and comes back up. I don't know. All I know is those 2 points exist. So what does it want me to say? What does the intermediate value theorem guarantee? Okay, remember the intermediate value theorem is the one that tells us that if I have a continuous function and I have a y value right here and a y value right here, then it guarantees that there is at least one y value in the middle of those 2 y values that an x gives you that y value. So let's write that out. So the intermediate value theorem guarantees that there is at least one y value between, what were my y values? 8 and -10. There's at least one y value that exists so that there is an x value that equals, oh, I better say, let's word this a little bit differently. There is at least one y value between 8 and -10 that exists so that there is an x value between -2 and 1 such that f of, well, that x value equals my y value, my h. And maybe we should have called these something different. Like there is a y value of h between 8 and -10 such that we have an x value between -2 and 1 so that it satisfies at some point I'm hitting that value. Remember, this was I was going 5 miles per hour and then I was going 20 miles per hour. So at least one time I went 15 miles per hour because 15 is in between 5 and 20. 19. Find the derivative if y e to the x minus x equals y squared. Oh, not just find the derivative, it wants dy dx. Okay, ooh, this will be a good one. We don't have to think too much, we just can derivative. We don't have to problem solve, we can just derivative. So, derivative of y e to the x. I've got to do the product rule. The derivative of y is dy dx multiplied by e to the x, plus the derivative of e to the x is just e to the x multiplied by y. And then I minus the derivative of x is just 1. And that equals the derivative of y squared is 2y dy dx. So this is one of those where we are trying to get dy dx alone. So I'm going to take this right here, and I'm going to move it to the other side. I want to move it over here. So I'm left with e to the x times y minus 1 equals 2y dy dx minus e to the x dy dx. I know some of you are cringing right now because I'm not doing y prime, but deal with it. E to the x y minus 1 equals, if I factor out dy dx, then I'm left with 2y minus e to the x. And if I divide that over, I get e to the x y minus 1 divided by 2y minus e to the x. All of that equals dy dx. And this should be an answer. But you could have also, maybe you moved at the very beginning. Maybe you took this 2y and moved it this way. So your answer might have ended up being, what? Positive 1 minus e to the xy over e to the x minus 2y equals dy dx. Those are the same answer. They're just written in a different way. So make sure if you get to the multiple choice and you don't see yours, double check and make sure it's not just written a different way. Basically, we took ours and we multiplied the top by -1 and the bottom by -1. So the signs changed. That's all we did. Okay, number 20, horizontal asymptotes. It's already a question you're going to love, right? Find the horizontal asymptotes for f of x equals 5x plus 2 divided by cube root of 27x cubed plus 1. Okay, when I see horizontal asymptotes, I am thinking two things. My limit as x goes to infinity and my limit as x goes to negative infinity. And then I'm interested in top heavy and bottom heavy. All right, remember, if I am top heavy, then my function, it doesn't have a horizontal asymptote. It could have what's called a diagonal asymptote, but it doesn't have a horizontal one. If I'm bottom heavy, that means that I go to 0. My asymptote is at y equals 0. If my coefficients, if my powers are the same, if I have equal powers on the top and the bottom, then I take the coefficients of my largest value. So when I look at this function, the first thing I notice is on top, all I have is a 5x. And you might be tempted to say that the bottom is bigger because it's bottom heavy. But look at this part right here. I'm taking the cube root of x cubed, and I know I have a plus 1, but as I go to infinity, that doesn't matter. As I go to infinity, that disappears. So I'm left with the cube root of a cube. So really the bottom, it's kind of like I have 5x on top, and if I cube root that cube, I have 3x on the bottom. So my powers are the same, which means that I'm going to be looking at my coefficients. So two things to consider, and I know a lot of times we've only looked at the positive, but we got to be careful. I want the limit as x goes to positive infinity of that 5x over 3x. Well, that becomes, as in the top goes to positive infinity, so I get a positive 5 infinity on top. On the bottom, I go to positive infinity, so I get a positive 3 infinity on the bottom. So I'm just interested in that part right there. I'm going to approach those coefficients. So I'm going to approach 5/3. All right? Now, as I go to negative infinity, which is the one that we forget a lot, I guess we should probably, my answer is going to change a little bit because I need to leave it cube root. I shouldn't have done that, simplifying, because that changes what happens with negative infinity. When I plug in negative infinity up on top, I go to a really, really big negative number, right? When I put negative infinity on the bottom, I cube it, which keeps it negative. And then I cube the cube root. Right? I cube my cube root, which makes my bottom negative because I have a negative and then I cube root it and I get a negative. So that one also ends up going to positive 5 over 3 because I get a negative on the top and a negative on the bottom. If I had had something like, let's just change this a little bit. Let's make it 5x over the square root of 4x squared. Let's just make it easy. If I were to have done this one, then my limit as x goes to infinity, the top is going to be positive, the bottom's going to be positive, so my limit's going to be 5/2 because the bottom basically goes to 2x, right? But as I go to negative infinity, my top goes to a negative. But my bottom, I square my negative infinity and it makes it a positive. So I get a negative on the top and a positive on the bottom. So I'm actually going to have two different horizontal asymptotes. I'm going to have one at 5/2 and one at negative 5/2. In our problem, the negative and the positive both took us to 5/3. So I don't have two horizontal asymptotes. I only have one. It's just 5/3. So y equals 5/3 would be my horizontal asymptote. All right, now that you are done having so much fun with that one, let's try these last two limits. Or I guess limit and then 22. Oh, look how nice I am giving you some L'Hopital. All right, the limit as x goes to 4 of x cubed minus 64. If I do direct substitution, 4 cubed minus 64 equals 0. 4 squared minus 16 equals 0. So by L'Hopital, I can take the derivative of the top and the bottom and do the limit as I go to the derivatives. So the derivative of the top is just 3x squared. The derivative of the bottom is just 2x. And as I plug in a 4, let's see, 4 squared is 16. 16 times 3 is 48. 4 times 2 on the bottom is 8. So the limit as x goes to 4 is 6. I only had to do L'Hopital one time. All right. 22. D squared y over dx squared. So what that means is it wants me to take the derivative twice. So x minus 6 over x plus 2. The first derivative, and let's just call this y. Y prime, I've got to do the quotient rule. So the derivative of the top is 1 times the bottom, x plus, what's happening here? X plus 2. Minus the derivative of the bottom, which is 1, times the top, x minus 6, all over x plus 2 squared. So that becomes x plus 2 minus x plus 6, all over the same. So I just end up with what? 8 on top. That's nice. So now when I take my derivative again, y double prime, I got to take the derivative of my derivative. So the derivative of the top is 0. So when I times it by x plus 2 squared, it goes away. Then I minus the derivative of the bottom is 2 times x plus 2 multiplied by the derivative of the inside, which is just 1. Then I have to multiply it by the top, which is 8. Geez. All over x plus 2 squared. So y double prime equals 0 minus... what? 2 times 8 is 16, so negative 16 x plus 2 over x plus 2. Oh, I forgot to raise that to the square again. So that's x plus 2 to the 4th, right? Well, that x plus 2 cancels with one of those, so I just get negative 16 over x plus 2 cubed. Becomes my final answer.